Recording in progress.
Okay, welcome to class. Welcome to class. Let me check really fast the checking prerequisite for Calc 1. 2 seconds. Let me see. And then we'll we'll continue with discrete math, talking about discrete math. Let me see. Right away, I'll get the Juby key. But yeah. Let me see. See there. There. Okay, let me check. Rafi Ahmed. Let me see. Rafi Ahmed. Gamwu. The things that if I don't have the prerequisite for Calc 1, I will drop you from the class. So let me see. There. And there. Brian. And then Francis, can you turn on your camera? Patel, Rohan, José, por favor. Gracias. And then Austin. There. Okay. So, Felipe, gracias. Gracias, Felipe. Let me see. I go in that direction. There. So I'm assuming that each one of you have you uploaded the prerequisite for Calc 1, that I can see it right there, because if I don't have it, my job is to drop you from the class right there. So make sure that you upload it, the prerequisite proof. So Austin. Allah, do you have your camera on? Let me check. Okay. Austin, grab your phone and enter through your phone. There is no way that your camera doesn't work, because you have a phone and you can put Zoom in phone right there. So please, Austin, re-enter the class with your camera on. Allah, re-enter your class with the camera on. Please. So I will re-enter you later. And let me check Allah. There. Perfect, gracias. So let me start. I'll go and share with you. There, share, and I'll go to at once. I'll go to OneNote.
Hey, Professor.
Yeah.
Someone's saying in our group chat that their Zoom is telling them they need permission to get in.
Okay. Let me check right away. Sometimes, let me see. I'll go there at once. It's only, yeah, it's a lot right there. Yes. And let me check. Thank you a lot. Thank you. So perfect. So if you see there in the chat that anybody needs permission to get in, tell me and I will let them in at once. Right there. So perfect. Let me go right away and get some notes for us at once. There. New. Well, I'll go back and then there. Perfect.
Excuse me, can I turn my camera off?
No, Allah, you can't. I'm sorry. It has to be on. It's a rule for the class. Yes.
Okay.
Yes. Thank you. Let me see. Yeah. Thank you a lot. Thank you for your understanding. So right there, it's last class we had. Oh, 2 students want to get in. There. There. Perfect. Okay. Last class we had something like this. P and P or Q equivalent to. Does anybody remember what it was equivalent to? P, gracias. Yeah, yes. Yeah, P. It was absorption. It just deleted the Q, and then of course we can show that that's true by truth table. So by truth table. So this is from section 2.1. 2.1 right there. And of course, the truth table will be PQ T TFF TF. And then of course we'll go with the OR, and that will be a bunch of T's since it's the conjunction, and F at the end. It's an OR statement. And then of course I'll put the P again and do the AND right there, and then here I'll do the P and P or Q. Right. So, and the P was of course TTFF. Right there. And when we do the AND between these two, right here, an AND between those two, we are going to end up with T right there, T and FF right there. And that vector, it's equivalent to this vector right there. So P, it's equivalent to P and P or Q. Okay with that? Okay, that's proved by, you proved it by truth table. So it's a proof by truth table. Proof, let me see, I'll proof by table, by truth table. There. The proof by algebraic manipulation, that's the next one. So this one is slightly peculiar, it needs a trick. So here it comes, proof by algebra. Right here, proof by algebraic moves. Algebraic manipulation. Right there. So it requires a trick. Here comes the trick. Anytime I see P, right there, anytime I see P, let's take a look at P and contradiction. Right there. So I have P. P is, right there, P or contradiction. Right there, let me see. There. I'll erase, draw, P or contradiction. Right there. So P could be true or false. And then I want to do P or contradiction. Contradiction is always false. And at the moment that I do P or contradiction, that is TF. So the trick that I'm going to use is exactly that one. Is this vector is the same as that vector. So P or contradiction it's equivalent to P. And that's what we're going to use in that problem. So to be able to prove absorption, and this is called absorption. There. Perfect. So let me see. I'll go here with absorption and prove it algebraically. Here it comes. So it's this one of P and P or Q. So our first move is going to be to replace the P by the P or contradiction. They're equivalent. And that's the trick right there. Now, I'll take your input. What would you do next? Right there with algebraically. What's your algebra feeling on what you should do next?
Can't we factor or use the distribution rule?
Yes. My gut feeling algebraically tells me that I should factor. Who said that?
That was me.
Thank you, Ansley. Thank you. Perfect. That's my gut feeling. I'll come right here. We always have a algebraic gut feeling. And just like Ansley said, well, look, we have right there P. We have right there P. It's a common factor. So we are going to factor P. Perfect. That's it. I'll do that one. I'll factor P. As soon as we factor P, what's the next symbol? I just wrote P. What am I going to write next right away?
Or?
Or, yes. An or right there. And then here will be the C and Q. Right there. So we're doing everything by algebra. This is pretty cool that we can do algebra because this is an algebra right there. It's a Boolean algebra. So we can do an algebra on those symbols. Then I need to go right away and try to act like you already know, but let's go to the side and compute contradiction and Q right here. So I will go to the side and I'll say, okay, what is contradiction? Let me see, I'll change the pen. There. Oh, it's black. Perfect. Contradiction and Q, a conjunction. What should that be equivalent to? Right there.
It seems like it should be equivalent to contradiction.
Yes,
Con-
Francis. Yes. Perfect. But of course, we can reason that. Look, it's an and with a column that has all F's. The contradiction has all F's, and you are doing an and. You're gonna get all F's. But let's make the table. So on the side, we'll say, okay, we'll try it. It's going to be a Q. A Q could be T or F. It's going to be a contradiction. That's always F. I'm going to do an and any statement and a contradiction is exactly what Francis said, is a contradiction. Meaning, it's a contradiction. It's all F's. Let me write all F's right there. Let me see, I'll erase. And I'll write all F's. So those two are equivalent. So, and that's one of the rules. It shows up. It shows up in the table of all the algebraic rules in section 2.1. So that's it. I'll continue right here. So it will be P or contradiction right there. And what is P or contradiction? Ansley answered that one some time ago, I think. P or I did with the table right there. P or contradiction is P right there. That's the table that we had up there. So let's put the two tables. So the trick, this was the trick on the proof, to use this. We know that algebra has tricks. Right there. And then we showed it right here with an auxiliary table. And we had this auxiliary table right there. But the rest was all algebraic moves. We distribute, and then we use those two rules from the algebra. Happiness with that. So it's a symbolic proof. So I can write here as desired, but we finish. And we put a little box. Our proofs are going to have sentences, our future proofs. But these ones are more like the logic proofs from the philosophy class, that they are more symbolic right there. So let me put a fence right there, and I'm going to write proof right here. We just showed it. Is there here proof? We proved absorption right there with those moves. Happiness with that. Right there, perfect. So the next section is the single most important section of the class. So section 2.2. Let me see right there. Section 2.2 is a conditional statement, and that's the most powerful statement in math, because it says P implies Q right there. So P, let me write implies. P implies Q right there. So we have a new symbol. The new symbol is this arrow that I'm putting right there. So I'll highlight the arrow. So somebody might consider that an operation. It's not. If it's an operation, any new operation in this algebra has to be a sequence of ands and ors and nots. So if I see a symbol like this, that new symbol, implication, that is so important, it has to be made up of ands and nots and ors, but has to be one of those. So let me go to the definition right away from the philosophy class. If they tell you that, supposing philosophy, they tell you that rain implies clouds. Right there. The existence of rain implies the existence of clouds. Suppose somebody says that. You can become the devil's advocate and say, one day when I was 7, it was raining and it was not cloudy. Well, that was an anomaly. You were maybe in Kansas and the wind from Missouri was bringing the rain. But no, if it's raining, the clouds created the rain right there. So it's cloudy. Happiness with that. Perfect. Here comes the definition from philosophy. It is not the case, that's the not, open parenthesis. It is not the case that I see rain and no clouds. Look, it works linguistically. They're equivalent, those two. Let me write it down. It is not the case that, it is not the case that you see rain let me put a parenthesis, and not clouds. I put the and from logic. And then close it right there. It is not the case that you see rain and no clouds. So that's it. I can give you the truth table for this new, I don't consider an operation, but it's a function of right there. It's a sequence of ands and nots that is very popular. So at once, I can tell you this. Anytime you see P implies Q, you can write automatically. It is not the case that I see P and not Q. Right there. And let me put it in a box. Do I memorize this? You bet I memorize this because I do memorize algebra, or something as important as this is huge. I'll go on. And then, of course, I will create the truth table at once. Right there for this. Again, let me just continue with this manipulation. P implies Q. If P, then Q. It is this. I'll write it again. And then another expression, I can distribute the negation. I can distribute the negation. What did we call our previous class to distribute the negation? What name did we give it?
De Morgan's.
Perfect. De Morgans. Thank you. Thank you. De Morgans. And that's what I'm going to do. Somebody might say I'm going to Morganize it right there. Distribute the negation. So let's Morganize it at once. It's not P or not Q, which is Q. So somebody might write it like that right there. It doesn't make sense linguistically, but it's definitely correct logically right there. Linguistics and logic should go sometimes hands in hand, but it will not, it doesn't have to always go hand in hand right there. And I know that linguistics has some logic in it, you bet. People that study semantics study this. This is on the first 3 weeks of a semantics class, what we're doing right now. So, but again, this sounds like not rain or clouds. It does. I don't speak that way. Not rain or clouds, but they're all logically equivalent. So we can make the truth table. So the truth table will be P, Q, and then the TTFF by convention. TTFF, TF, TF, and then I'll do the no Q, F, T, F, T, Right there. Then I do the P and not Q. So I'll bring the P again. I'll put it right next to it. I don't need to, but just in case. And then I do the P and not Q. P and not Q. So the P and not Q is going to give us F. T. Let me draw that F a little bit better. The F. T. F, F. Okay. And now if I put the negation, right there, it will be T, F, T, F. And that's it. That's the operation implication. So that one that you have right here, allow me to put right here, not P or Q. That's going to look the same. TF, TF. Oh, TFTT. There. I was doing the and. See, oh, I'm sorry. Let me draw it the same way. There. I should have only one F. So I'm doing the P. There. I was doing the and. I was doing, oh, let me erase it. There, I'm doing the not of this column. So the not is going to be T, F, TT. Right there. And that's the sequence, 1, 0, 1, 1. And that will be the same as this one if you go and check. TF, TT. And that will be equivalent to the implication. Then we'll go and talk about it. The implication here will be P implies Q will be T, F, TT. Right there. So these three are equivalent. There. Those three are equivalent. What do we get here for free? That is very important. We get at once. Let me highlight this. At once, I get the negation of the implication. I get the negation of the implication at once because that's a double negative on that fourth column. Let's just talk about it. Suppose somebody tells you, somebody says, if marriage, then love. What is the negation of if marriage, then love?
Is it just if not marriage, then not love?
No, but let me write it down. Let me write it down. The answer is no, but let me write it down now, at once. Because I would have said that. Right there. Let me just, if not marriage, then not love. And let me put there not equivalent. Right there. And thank you. Yes, I needed that. Right there. I would have said the same thing. The negation, let me do it with rain and clouds. If rainy, then cloudy. the negation is I see rain. So the hypothesis happens. The negation is the hypothesis happens. I see rain and no clouds. I see rain and no clouds. That's the negation of when you tell me, look, every single time it's rainy, it's cloudy. I will tell you no. One time in Kansas, at Kansas State, I saw rain and no clouds. Right there. I would have said exactly that. But you have it. You have it on that column. Let me go to the column at once. So the negation of an if-then is never an if-then. You see, I don't have ifs. I don't have thens on the negation. Let me go all the way up here. Look what the negation looks like. I see rain. Oh, I'll draw it. Let me see. There, red. I see rain. And no clouds right there. So perfect, perfect. That's important because we're going to do proofs by contradiction. And we need to be able to write the negation at once right there. So perfect. So there. Okay, let me put a fence. And now let me tell you the way Susana talks about this. I went directly to the definition of the conditional statement. But here it comes. When we say this, if P then Q, P implies Q, right there. Here it comes. I'll put the P, T, T, F, F, the Q, T, F, TF, and here comes the implication that we got by that definition. We got T, F, T, T, right there. So, in this particular type of statement, the hypothesis must happen. The hypothesis is achieved, and the conclusion better follow. And Susana, in the textbook, has an analogy. The analogy is this. Somebody's going to give you a new job, and she says, if you show up at 5:30, comma, then the job is yours. There. So the hypothesis, the P is called the hypothesis. The conclusion, the job is yours. Right there. Hypothesis and conclusion. So, suppose you show up. When can we call this person a liar? The person that told you that statement. When can we call her a liar? Let's check. You show up. That's the hypothesis. You showed up. And then she gives you the job. Perfectly okay. Perfectly okay. That's true. You show up at 5:30. You had to drive, take a shower before. You show up at 5:30. And then she doesn't give you the job. Can you call her a liar?
Yes.
Yes, 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 yes. So there, liar, right there. Because you showed up and she didn't give you the job. So that's false. Now, you don't show up and then she calls you at noon and she tells you, I'll give you the job. Show up. We need you. Show up at any time. Can I call her a liar?
No.
No, because the hypothesis was not realized. So look at here, these two. Right there. The situations where you don't show up, they're always true by default. It's called vacuous truth. The hypothesis was never achieved. Okay, with that, I need a logic that has two values, ones and zeros. This is vacuous truth. Vacuous truth. And the implication is always true. When I see an F for P, automatically I jump and write the T here. Automatically. Because it's an F on the hypothesis. Happiness with that. Perfect, perfect. Look, I'll give you another example. If Pelican in the classroom. Now, in our Zoom class, if there is a Pelican right now among us, okay with that, if there is a true Pelican among us, then we'll get the money to go to Miami tomorrow. All of us, Miami tomorrow. For all of us, Miami tomorrow. For all of us. Right there. There is the hypothesis, a Pelican, and there is the conclusion. I had one time that student showed me a keychain that had a Pelican. So I owe the tickets to the entire class to go to Miami right there. But look, that is a vacuous truth. That is a vacuous truth right there. Okay. I could say it that way. I could say it with a universal statement. All Pelicans in the class right now will go to Miami tomorrow. So that's equivalent to all Pelicans in class. Well, in class. Well, that's not, because I said all of us. I should have made it about the Pelicans only. I should have said, if Pelican in the class, those Pelicans will go to Miami tomorrow. That would have made it a better vacuous truth. Let me go and fix it. Because I want to turn it into a universal. So if Pelican in class now, then those Pelicans, or Pelican, one or more, those Pelicans will go to Miami tomorrow. Perfect. So look, it's a vacuous truth. There are no Pelicans right there. And then let me write it as a universal statement. Sometimes we can do that. Right there, all Pelicans in the classroom will go to Miami tomorrow. There. So that is a true statement. It's a vacuous truth. It's not very interesting, but it's true. It's true. Because you are, let me give you another there. We'll go to Miami tomorrow. There. The way my wife will translate this, she will say, because she comes from linguistics, she will say, you can say anything you want to about the empty set right there. Because look, the hypothesis was not realized. So then she will say, you could say anything you want to about the empty set. It's a true statement, but who cares? Okay with that right there. Like for example, I could tell my wife, look, if I organize the garage today, we'll go to Red Lobster tonight. So then my wife will be, that's a vacuous truth, because you will not do that. You will not organize. So it's a true statement, but you will not go to organ. The garage is not that bad, but still, I could go and organize. But I'm busy during the semester. I'm not going to enter the garage. Okay with that? Happiness with that?
Question.
Yeah,
I got a
go for it,
question.
Brendan.
So is the term vacuous truth applied to the hypothesis or the whole statement?
It is applied to the whole statement. It's applied to the whole statement, but what's vacuous is the emptiness of the hypothesis right there that makes it work.
Thank you.
The first time I heard this, I felt like changing my major for like 2 hours. And then I said, it's going to be okay right there, because we're not talking about vacuous truth all the time right there. Okay, yeah. So it's not that bad. We have to have it. I have to have it right here. I have to have it in that system, because if the hypothesis is not realized, it has to be true. But again, the things that we're trying to prove, we assume the hypothesis and we try to move to the conclusion always on all our proofs. So if somebody tells me something like this, let's say something that we were going to prove in the future, it will say if x is even, so I'm talking about integers. If x is even, comma, then x squared is even. Right there. If I want to try to prove that, right there, I'm going to assume the hypothesis. So it's not going to be a vacuous truth. My first statement will be prove. Let x be an integer, because I'm talking about even. So better be an integer. Let x be an integer. Comma, and assume x is even. Perfect. And then I will continue with the proof. Can you see? I'm assuming the hypothesis. There is never going to be a situation where I am not assuming the hypothesis. Okay with that? So, big deal. I need to know the existence of vacuous truth, but I don't. I will use it in a proof in the future, but there are very few. So I'll finish the proof right now, because we're going to write proofs. The next thing I will use is the definition of being even. So here, by definition, we'll see this very soon in chapter 4, but this is really easy to understand. By definition, comma, x, it's equal to 2k for some k in the integers. Right there. Can you see? That's the definition of being even from any math class that you would have taken before. Any even that you have in your back pocket, it's 2 times an integer. It has to be your favorite even integer, has to be 2 times something. Happiness with that? Perfect. And now I'm going to do some algebra, because all of these proofs have to have some algebra. Consider x squared. And I will show that x squared is even. So period right there. I'll consider x squared. I want to show x squared is even. And I'll do it right now. So x squared, it's equal to x times x. It's equal to 2k times a 2k. Right there. 2k times a 2k. And then I need only 1 2. I don't need the 2 2's. And this is equal to 2. And look at the amount of associativity I'm using. 2 times 2k squared. Right there. So 2 times 2k squared has to be an integer because it has a 2 on the front. But also, I need to say something about closure. Every time you multiply integers, you get integers. Okay with that? So we need an axiom right here in this proof. What happens when you multiply integers? You get integers. But you're not going to get a rational number. You're not going to get the square root of 2. So, and again, remember, the definition says there that k is an integer right there. So perfect. Right here, we can say, see that 2k squared is an integer. By closure, or it's an integer because the set of integers is closed under multiplication, under products. Right there. So I needed that axiom. Closure means that you have an operation, you have 2 elements, you compute that operation, and you get another element from the same set. Can you see what I'm saying right there? It doesn't happen with vectors necessarily. The dot product, when you compute work, if you're taking a physics class and you compute work, you take the dot product of 2 vectors and you get an integer. So under the dot product, those vectors do not have closure because you use that operation dot product and you get some other object that is not a vector. Under the cross product, right there from your physics class, under torque, the cross product, you cross 2 vectors and you get a vector. Can you see what I'm saying? Right there. So perfect. So then, hence, x squared is even. I was able to write it as 2 times an integer. So I will say that we were able to write, let me say that. There, we can write x squared as 2 times an integer. Hence, x squared is an even integer. And then, as desired. And the little box. Right there. The whole purpose of this class is proofs. So I just gave you one right there, but we're going to do tons of those as we move more towards chapter 4. Okay with that, but I put one right here. I needed to tell you that we always assume the hypothesis, so you don't feel that you need to change your major after seeing vacuous truth. I don't want you to change your major or become a philosopher right there, because then they might deal with more vacuous truth right there. I read books in philosophy that there were 400 pages, and that at the end of finishing the book, I didn't know anything. I'm like, what did I learn? Nothing right there. So that happens sometimes in some classes. Okay with that? I read a book by John Dewey, 400 pages, and I got nothing. So that's not going to happen with this class. I promise you. Happiness with that. And maybe I got nothing because I didn't have enough wisdom at the time that I read it. And if I read it again with more wisdom, I will get something. Okay, maybe it was my lack of wisdom. Happiness with that. Perfect. Okay, let's continue our journey. So, right here. So, every time we negate a P implies Q is you cannot write an if, you cannot write a then, is the hypothesis happens. Let me say it. There. The hypothesis happens and the conclusion fails. That's the negation. I keep doing that. The thing is, after teaching Calc 3, many times I'm brain dead, and I'm teaching Calc 3 before this class. So, perfect. Let me put it right there. P happens and Q fails. Right there. P happens and Q fails. So, that's the negation at once. So, what would be the negation of the thing that we already proved? It's a false statement, of course. The negation of what we just proved, that's true. What we prove is true, is X is even and X squared. Oh, it tells me that the battery is low. That's not true. My battery is full, I promise you. It's connected right now. So X is even and X squared is odd. That's false. It's a false statement. Let me see. There. Oh, it might feel that the pen. Let me put the pen for 2 seconds in the thing to charge. 2 seconds. Right there. So I'll go and fix it. Oh, I have another pen. Let me see if this one works. Right there. Yeah, it does. There. So I'll use my other pen. Right there. There. So X is even and X squared is the negation. It's not even, it's odd. Right there. Of course, this is a false statement. Because we just proven if X is even, then X squared is even. Perfect. So let me put right here. Sometimes I have to write proofs like this one. If X squared is even, then X is even. And of course, we're talking about integers. And it turns out, and this looks like a P implies Q right there. Now, it turns out that this is very difficult to prove the way it is. This is the P. This is the Q. And you're taking a math class and you get stuck. And it turns out that this statement is difficult to prove. What's your tool? What's the tool that you have from the logic world? The contrapositive. The contrapositive comes to the rescue. Let me write the contrapositive of this statement. The contrapositive is a tool of the mathematician, of the engineer. So the contrapositive. Right there. The contrapositive is, if you have P implies Q, the contrapositive is not Q implies not P. Right there. They're equivalent. So, if marriage then love, it's equivalent to what statement?
If not
If
love,
there's-
then not marriage.
If not love, then not marriage. Yes, 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 yes. and that's the new hypothesis, and that's the new conclusion. So many times in a math class, proof-based math class, you have to prove something that the hypothesis is more complicated than the conclusion. Look at this statement. X squared algebraically is more complicated than X. So can you see, I learned X first, then I learned X squared. And it should be that always the hypothesis is simpler than the conclusion. So I will use the contrapositive to my advantage, and I will prove that a lot faster. This is 8 pages trying to prove it in the direction that it is right now. So use the contrapositive, because nobody wants to read your 8 pages when you can write it in 3 sentences. So use the contrapositive. So I will write the contrapositive at once. If X is not even, then X squared is not even. Okay with that? So let me circle that. So the contrapositive for this will be, oh, let me erase there. I'll write it again. It will be, I'll write it right here. So super difficult, and create new notation. If X squared is even, then X is even is logically equivalent to if X is odd, comma, then X squared is odd. Let me erase there. There. Red. And this is super simple. Right there. You prove it exactly that the proof that I did before. Right there. Because let me just give you how to prove it. I will not write it, but I can tell you can write the same sentences. Assume the hypothesis. So this is the jot. It's not the formal proof. I wrote a formal proof before, the one above. But I'll give you the jot so you can construct the proof for fun. Then we'll do it. We'll do it in 3 classes. So this will be X, it's equal to 2Q plus 1 for some Q in Z. Right there. An odd integer is 2Q by definition. An odd integer has remainder 1. Mean an odd integer will have remainder 1 when you divide by 2, always. And that's a remainder, 1. So then once you have that, you are assume this, try to write X squared as 2 times an integer plus 1 when you do the algebra, and use the axiom that the integers are closed under multiplication. Can you see what I'm saying? It's a very similar proof. And it was impossible, almost impossible to do the way it was before. But applying the contrapositive brings you to the rescue. Right there. Happiness with that. Perfect. So I'll put a fence. So P implies Q. It's equivalent to the contrapositive. Not Q implies not P. Now, sometimes they're going to tell you, okay, what about Q implies P? So they decided to reverse the direction. It was if rainy then cloudy. They decided to do if cloudy then rainy, which we know is false right there. But this is called the converse. Converse. So I'll write a full sentence. The converse of P implies Q is Q implies P. Right there. You want to go in the other direction. So you are talking to another computer science major or math major, and she tells you, let's look at the converse, that means that you're going to swap the directions right there. Or is the converse true? Is the converse true? So you swap the directions. Sometimes it could be true, sometimes it could be false. Right there, we do not know. Happiness with that. So we have a language to reverse the direction, to go in the other direction. It's called the converse. Perfect. The next one is called the inverse. So we have the contrapositive, the converse, and the inverse. The inverse is not P implies not Q. So let me write a full sentence. The inverse of P implies Q is not P implies not Q. Right there. Okay, with that, happiness with the definitions. Those are definitions. There's nothing I can do about it. I impose on us. So we memorize them. We memorize the definition the way that we memorize algebra. Right there, because these are algebraic moves. Right there. Perfect. So what can you tell me about the inverse and the converse? Look at them. Oh, I'll switch pens again.
The converse is just flipping the entire thing, whereas the inverse is changing the polarity.
Oh, no. I'm telling you a relationship between those two, a relationship between the converse and the inverse.
The inverse is the contrapositive of the converse.
You nailed it, Francis. Yes, and I would love to have a sweatshirt, a hoodie that says that, or a bumper sticker. I would love to have a bumper sticker that says that. Let me, can you say it again to us, Francis?
The inverse is the contrapositive of the converse.
Perfect. The inverse is the contrapositive of the converse. That would be a super cool hoodie right there to say that on the back. Okay with that? Okay. Happiness, and since we're in Austin, we can wear the hoodie all year because we're inside with air conditioning. And sometimes the air conditioning is freezing. So we can always have a hoodie on all year. Okay, perfect. Okay. Thank you, Francis. Right there. Okay, there. Let me see. Okay. There. Sometimes they do this, and I don't like when they do this. They do Q if P. In some math books, they might write Q if P. What do they mean when they write Q if P? If P, then Q. They mean that. Okay, without anytime they write Q if P, they decided to put the hypothesis at the end, right there. Happiness with that. Right. Well, I'm not happy, but I accept it right there. So every time I see Q if P, they mean P implies Q. Right there. They mean P implies Q. It means if P, then Q. If P, then Q. Right there. Sometimes they write this. P only if Q. Let me put a fence between those two. Sometimes they write P only if Q. What do they really mean when they write that? Let me put a little. They really mean this. Anytime somebody says P only if Q, means that if you don't have Q, you don't have P. That's what they mean every time they say P only if Q. If you don't have Q, you don't have P. And what is the meaning of if you don't have Q, then you don't have P?
I'm sorry, can you repeat the question?
Yeah. How, can I simplify no Q implies not P?
Is that P then Q?
Yes. If P, then Q. Yes. Gracias. Perfect. So that's it. Right there. So that's tricky because in some situations you need to prove statements that they have been written that way. Happiness. Okay, now let me go right away and try to pick up a problem at once from the textbook. So look, if I go right away to Blackboard, you have that immediate homework, and the immediate homework is talking about this. Let me go right there. Go to the immediate. There, Gradescope. Gradescope is the immediate homework. And if I click on the Gradescope homework, that is due in 2 days, it's due the 30th. It's exactly what we're doing right now. Okay, with that, you have an implication and then another implication right there, and determine if those are logically equivalent. So do it by table right there. That could be helpful. But you can also do it by algebra right there. It will work to do it by algebra right there, because if well, let me go and give you an example by algebra. And then this one right there, simplify that statement by distributing the negation and so on. And then there, show that those are logically equivalent. Show that those are logically equivalent. You can do it by truth table, perfectly okay. And then that's it, those. But let me play with the contrapositive. I could potentially get stuck, but first we can try with truth table right there. Super fast. Let me see. I'll go back to right here. Suppose we have something like this. And we want to show that this is equivalent to this. Right there. I can definitely do it by truth table first. Right there. It will be P, Q, and then the T, T, F, F, T, F, T, F. And then we already know this one. P implies Q. Is T, F, T, T, vacuous truth, the last two. But now I will write my not Q. And the not Q is FT, FT. And then I will write my not P. And my not P is FFTT. And then I will write my not Q implies not P. I will highlight the F on the not Q because those will be vacuous truth. So once I'll highlight this, that's a vacuous truth, and that's a vacuous truth. So I will put these on those automatically. I could care less what it says on the conclusion. And then take a look at this one. T implies F. That is F. And the last one, T implies T. That is T. And I'm looking at this vector. And this vector is equivalent to that column vector. 1, 0, 1, 1. They are logically equivalent. And I just showed it by table. Okay with that. So that was by table. Was a tabular proof. Right, a truth table. Is doesn't want to write. Let me see. But erase. There. Proof by truth table. Now, if I want to try to do this algebraically, let me check. I need to jot because I'm going to do algebra, so I might have to erase. So there is the jot I'm playing with first, right there. And we want to show that P implies Q is logically equivalent to not Q implies not P. I need to start somewhere. Potentially, let me, by chance, start right there and see if I can go to P implies Q right there. So I am going to use the definition from logic. Remember, the definition was P implies Q. It's equivalent to. It is not the case that P happens and Q fails. And I can also use the definition that is not P or Q. I want to use that. So I put it there on the back burner right there. It's not the formal proof. I'm playing with it. Then I'll write it formally right there. Many times I have to do that. So let's take a look at this one. That's equivalent to negate the hypothesis. So I'll proceed to negate the hypothesis. This is the hypothesis. Negate the hypothesis. That would be a not Q, which is a Q. Or leave the P by itself. Right there. Or leave the P by itself. Can you see what it looks like? Can you see that I just proved it? I just proved it. Now let me reverse the order. The order is not P. There. There. Okay. There. And then I'll search for our textbook at once. Perfect. Right here. And then I'll run to section 2.2. To the exercises, conditional statements. And then I'll grab a problem at once. There. Okay, here. There. Perfect. 45. Right there. I'll grab it and put it on our notes. There. And I'll bring it to our notes at once. I'll put it right here. Control V. And then the last concept. And then we have super freedom. P implies Q. Every time you see P implies Q. The English major, that they do logic also, she could say this. P is sufficient for Q. This is logically equivalent to saying this. P is sufficient for Q. That means that the knowledge that P has happened is sufficient to know that Q has to follow. Okay with that? And she will say that. So rain is sufficient for clouds. The existence of rain, it suffices to guarantee the existence of clouds. Can you see what I'm saying? And then this is logically equivalent to Q is necessary for P. Right there. Q is necessary for P. So because the clouds are necessary for rain, always. If not clouds, then not rain. Happiness with that. So I will put this problem as an immediate, is one and only one problem. I will put it at a grade scope. Try to solve that problem, one and only one problem about translating this to P implies Q. Translating this problem to the language of P implies Q. It was in the language of next all of this. That's a leopard from Namibia. That's really cool.
Also,
I love
it's so-
Namibia. Yeah, go for it.
Also, is the part 1 homework due every 2 weeks?
It will be approximately every week, every 2 weeks, right there. And the grade scope, it happens more often than that, right there. So that's the part 2, because it's a shorter homework. It has only 3 problems. I'm going to write one that has only 1 problem, right there. Okay with that? So this one is the grade scope. It's super fast because it's only 3 problems, right there. And you upload this, you solve them right here, you solve them right under it. So you print this, solve them right under it on that page, and upload them, because that's the way Gradescope will give them to me to be able to grade. But now the other homework, the box, the homework box, that one right there, it's longer. It is a lot longer. So it's actually slightly more than a week. So it will be a week and a half.
Okay.
And then what was the homework that you saw? Because we only have 2 types of homework.
Okay. It was in course materials.
Oh, no. That's for you to explore. That's kind of like enter the course materials as if it was like a flea market. You go right there and just find new examples that they are not in the textbook. And I used many classes ago.
Okay.
So it's a surprise place where you can actually find the same knowledge, but not organized. The lectures are organized and the notes are organized, and the older lectures are organized. The course materials is just surprising.
Okay.
Okay, if you want to push the limits.
Okay. That was
Perfect. Yeah, so ignore it. That one, ignore it. Yeah, anything from course materials, ignore the assignments. So any other questions? Super freedom. Take care.